I was initially planning to do a whiteboard talk, but they asked me to do a tablet writing talk instead. And when I say AI is electricity, I mean that similar to the rise of electrification starting about 100 years ago, which transformed every industry, healthcare, transportation, manufacturing, agriculture was transformed, the rise of electricity started 100 years ago. AI has reached a point of maturity where we see a surprisingly clear path for it to also transform pretty much every major industry. And as I was preparing for today's presentation, I was trying to figure out what might be most useful to share with you today. And I thought what I'd do is present to you an overview of some of the things happening in AI broadly, and then drill down on a couple examples, case studies in healthcare specifically, and then also talk about some of the things I think the future might bring in healthcare. So despite all the excitement about AI, it turns out that 99% of the recent wave of value in AI is created through one idea, and that's learning input to output, or A to B mappings. And the technical term for this is supervised learning. For example, for a long time we've had AI that could input an email and output 0 or 1. Just tell me, is this spam or not? And thanks to the recent rise of neural networks and deep learning, this now works much better than ever before. I would say probably not the most inspiring, but the most lucrative application of this today is probably online advertising, where all the large online ad platforms have a piece of AI that takes as input some information about you and some information about an ad, and tries to figure out if you will click on the ad and sort of output 0 or 1. Working speech recognition, right? And I'm actually encouraged by the rise of speech recognition in the use of healthcare as well, right, for medical transcripts and so on. And a lot of the rise in speech recognition capabilities was this input to output AI, or the supervised learning AI, that can take as input an audio clip and output a text transcript. A lot of discussion about the role of AI in radiology and pathology, and that is a piece of AI that inputs maybe an X-ray image or a CAT scan or some other input, and outputs a diagnosis or outputs some other things about the radiology image. I don't know, jumping around industries. I'm on the board of a self-driving car company, Drive.ai. One of the key components of a self-driving car is a piece of AI that takes as input a picture of what's in front of your car, and maybe the radar readings or the LiDAR readings, sensor readings, and it outputs position of other cars. And one other case study you see in a little bit is palliative care, where my team at Stanford is working on taking as input, electronic health record, and trying to predict, right, mortality, 0 or 1. What is the chance that this patient will have a mortality event in next year, and this can be a way to recommend for consideration certain patients for palliative care consultation. So despite all the hype about AI, a lot of the 99% of the recent rise of the wave of value created by AI, and by value I mean economic value, social value, making human life better, a lot of this is just this idea of input to output mappings or supervised learning. And it turns out when you find the right business context or the right product or the right application context in which to fit this idea, it turns out to be incredibly valuable. AI is bigger than this, but I think for all of you looking for opportunities to apply AI to your work, this one idea still has a lot of room to run, although of course there are other ways of technology that hopefully will come online as well. Now, what I want to do next is something slightly different. So as I was preparing this presentation with my students earlier this week, we sat down and my students said, wow, there are a lot of important people in the audience here in person and watching this by the live stream. And one of my PhD students, Pranav Rajpurkar, wanted to do a live demo of one of the AI systems that were built in collaboration with Matt Lundgren, who's a faculty over in medical school to collaborate with, on this Xray and AI application. So here's an X-ray film. We've cut away some parts to remove PHI, and what Pranav will demo is an AI system applied to whatever it wants to do with this particular X-ray. So take it away from it.
Thank you, Professor Ng. So here's an X-ray film that I have, and most of the world has films rather than digital photographs as the way to take X-rays. And 2/3 of the world doesn't have access to radiology diagnostics. But imagine a world in which anyone in any part of the world could take a photo of their X-ray film and have an algorithm make the diagnosis of what that X-ray has in terms of the abnormalities. Now, some of the work going on in our lab is looking at diagnosing chest pathologies of X-rays. And today, I'm going to show you a demo of that, where we're going to take a picture of this X-ray film and see what we can find. So here is me trying to take a picture with the iPad. You can see Professor Ng there. And what we're going to do is position this film. I have a white background, and I'm just going to put the X-ray over it. And now I'm just going to position it so I see the full X-ray here, and snap. There's my picture. I'll take one more. There we go. And now I'm going to open up an app. So this is an app that we've built where we're going to find out what the algorithm says this X-ray has. So first things first, if we actually look at the X-ray and if we ask a radiologist to make a diagnosis, they would say that there's an enlarged heart here. It's a case of cardiomegaly. So we're going to see if our algorithm could have come to the same conclusion. So here I click Upload, and I'm going to use the picture that we took. And now it's running through the algorithm. And on the right, we see it's come out with all these pathologies. And on top of that is cardiomegaly, which is the enlarged heart. So the algorithm got it right. Now, if you're a clinician or a doctor in a different part of the world, you might want to know, hey, is this algorithm looking at the right thing to arrive upon its final diagnosis? And towards that goal, what we have also done is the ability for the algorithm to be able to show exactly where it's looking at when it's coming to its diagnosis. And here we can see that the algorithm is looking at the heart. I guess we can say its heart's in the right place. And the real goal of this is we hope that this will increase radiology access across the world. So that's my demo. Thanks.
Thanks, Ron. Thanks a lot, Pranav. So, all right, great. Let's switch back to the iPad. OK. So it turns out that a lot of the ideas of supervised learning, excuse me, just get this out of the way. OK. Turns out that a lot of the ideas of supervised learning, input-output or A to B mappings, have been around for a long time, literally decades. And one question a lot of people ask me is, hey, Andrew, why are these ideas only taking off now? And when people ask me that question, there's one picture I draw that hopefully that tries to explain. Let me just draw that picture for you now. If for an application, if on the horizontal axis you plot the amount of data, and on the vertical axis you plot the performance, such as, by performance I mean accuracy in rendering diagnoses from X-ray or for these other applications, accuracy of speech recognition and so on. It turns out that for the older generations of AI algorithms, the performance kind of looked like that. Right? Technically, it's an older AI, older machine learning algorithms. And even as society marched to the right of this curve, even as thanks to the Affordable Care Act, we transitioned to increasingly electronic health records, and in other industries, as these pieces of paper turn increasingly into digital records, even as we got more and more data for a lot of applications, the performance of our AI systems was not getting that much better. And what happened starting about, I don't know, 5, 6, 7 years ago was the rise of neural networks or the rise of deep learning. And what we found was that if you build a small neural network, NN stands for neural network, its performance sort of maybe looks a little bit better. If you build a medium-sized neural net, performance maybe looks like that. And if you build a very large neural net, this performance sort of keeps getting better, usually until it hits a ceiling on performance, which is often at about an expert expert radiologist rate, or sometimes even a little bit higher. But there is some ceiling. It can't do better than 100%, or sometimes it can't do much better than even the best radiologist. So sometimes there's a ceiling on performance. And I think that the two biggest things driving the recent rise of AI, of supervised learning, input-output A to B mappings, is the rise of huge data sets, as well as the rise of computational scale. So if you look at this chart, it kind of implies two things, which is that if you want to get the best possible performance, then it does help to have a lot of data, and hence, I don't know, big data is one of the buzzwords that's been going around. And second, you need large-scale computation to process all the data you now have, hence the rise of large neural networks. But with the rise of GPU computing, really, I think NVIDIA, as well as Intel and other companies, are doing a great job speeding up networking, speeding up compute. We now finally have the processing power to process these huge data sets that you now have access to. Now, this, I think, explains a lot of the recent rise of supervised learning. And if you read in the media the term deep learning means almost exactly the same thing as a neural network. It's just that in the AI world, we found that deep learning is a better sounding brand. And so that's the term that seems to be rising right now. Now, if you're sitting there wondering about applying this to your own problems, one piece of hype that has gone around that I think is unhealthy is the mystique behind having huge data sets. And so I've had doctors ask me, you know, hey, Andrew, I'm a doctor, I work in a hospital. Could I possibly have enough data to compete with the giant internet companies? And it turns out that data is very verticalized. And I think for brand new applications, even a small research group, like, you know, or a university, can get enough data to build something very meaningful. Let me illustrate one pattern I've seen draw an example from a different industry, and it will say how it applies to healthcare. So one pattern I've often seen is that a team, through, you know, just sweat, would collect small data sets, and this allows you to build an initial product, and this allows you to start to get some users, and having users increases the amount of data you have, and this virtuous cycle allows you to get more and more and more data. So here's one example from outside healthcare. Several months ago, there was a company called Blue River that was sold to John Deere for about $305 million. And an early stage of that company was like a class project in my machine learning class at Stanford. So I knew the students when they were, you know, students here at Stanford. So Blue River had built a machine, giant machine, that moves over agricultural fields and take pictures of the crops, and then simplifying the story a little bit, take pictures of heads of cabbage half buried in the dirt, and then makes decisions about what head of cabbage, or actually what weed to let live and what to kill, right? And so and it turns out that you can build a machine like this using computer vision to get rid of weeds or kill the appropriate heads of cabbage. This increased crop yields, and it's actually quite an interesting business. I know that in the healthcare world, we often talk about ethics in AI, and can AI make life and death decisions? So this is life and death decisions using AI for heads of cabbage. But what they did was, you know, when they were students at Stanford, they took their personal cameras out to the fields, and they just hunched over and just took a lot of pictures of these heads of cabbage. And so they started off with a small data set. And based on a small data set, they were able to build a product. It wasn't a great product initially, frankly. I saw, you know, the wire together, the wires hanging out. Like, it was like, okay, good enough to get some farmers to accept it. And once you have some farmers using the product, once these machines are running up and down the fields, then by the nature of doing the work, you just get more data, and you enter this virtuous cycle where having more data through AI allows you to build a better product, where you're better able to make judgments about what is a weed and what is a cabbage. having a better product allows you to get more users, and having more users allows you to get more data. And it turns out that if you look at, say, I don't know, the large web search companies, right? Even the giant web search companies don't have, as I would guess that today, Blue River has a bigger data asset of pictures of heads of cabbage harbored in the dirt than even the giant internet companies. And this actually lets them do a lot of things that I think even the giant internet companies would have a hard time doing. And I think this is why also of the giant internet companies moving into healthcare, we see the giant internet companies entering very sophisticated strategies to acquire data in order to build up this asset for themselves. Now, what I want to do just is present, I want to also, so I think that this playbook can work in healthcare as well. So today, I don't have enough data. I have a very good sense of how web search technology works, but I don't have a data asset of what users click on to build a web search engine myself, right? Now that I'm not wearing a Google or Baidu hat. But I think that in healthcare, there are a lot of verticals where for your application, you actually have more data than anyone else, or you have as much data as anyone else, and that allows you to build a very meaningful application. So I want to ask different PhD students, Anna and Avanti, to actually tell you about the second case study of when we're starting to build these types of applications and to deploy in palliative care. And I think we've been so fortunate to work with so many great collaborators in medicine. And so this is work with Stephanie Harmon, Kenneth Jung, and Professor Nigam Shah. And Anand will present this case study.
Hello, everyone. First, I would like to talk about what's the motivation behind the study? What's the problem that we're trying to solve? Vast majority of Americans prefer to spend their final days at their home, but only a small fraction actually do. More than half of the deaths in the United States happens in an acute care hospital, and most of the times, patients in their deathbed are still receiving aggressive care. Many patients on their deathbed do not even have their advanced directives or goals of care recorded, which is like a guideline for treatment doctors. We believe the cost for this is kind of twofold. So first is the treatment doctors. They always do a good job. They tend to be over-optimistic by nature, and studies have shown that doctors tend to be systematically over-optimistic about prognosis timelines.
I was told to tell you to hold it up to your mouth. Okay.
Okay. By a factor of up to 3 to 5x in predicting time to mortality. On the other side is palliative care teams. They generally tend to be understaffed, and in order to, for example, a palliative care team to proactively chart review all the admissions that are happening in the hospital and reach out proactively, that's hard as well. So the intervention here is to build a machine learning model, take a supervised learning approach. We build a machine learning model to train in a way where we feed the electronic health record of the patient, and the output is a probability of whether the patient is going to pass away within the next year or not. And we use this prediction, which predicts mortality, as a proxy for deciding whether the patient has palliative care needs. This enables a new dynamic within the hospital setting, where traditionally the referral process has been push only, where the treatment doctors refer a patient to palliative care upon their discretion. But this allows a push-pull model where palliative care teams can proactively reach out to treatment doctors and have a conversation with them of whether a palliative care consult is appropriate for that patient. Some results from our model. It performs well on our test sets, and currently it's deployed in a pilot mode at Stanford Hospital. Along with this, we also generate some explanations for what the model is actually looking at when it's making these decisions. So on the left column, we have different categories, diagnostic factors, procedural factors. These are all data in the medical record of that patient. And we also have a score and sort them by the score. And this gives you a sense of what the model is actually looking at within the patient's medical records in order to come up with a probability. So this is an example where the patient was given like a 0.94 probability. That's it. Thank you.
So let me wrap up with two final thoughts, and then we'll have actually plenty of time for your questions. I'm very excited about the potential of AI to transform healthcare, and I think that over the last few years, I spent a lot of time, studying the rise of the internet. Right, the internet was a major disruptive technology that transformed a lot of things, and there were some lessons I learned watching the rise of the internet that I think will apply also to the rise of healthcare, to the rise of AI, excuse me, and that I want to share with you. So, one of the lessons we learned watching the rise of the internet was if you take your favorite shopping mall and you build a website for it, right? Like my wife likes Stanford Shopping Center, so think of your favorite shopping mall, right? Build a website for it, have them sell stuff on the website. This does not by itself turn that shopping mall into an internet company, right? And in fact, about 5 years ago, I was chatting with the CEO of a large US retailer, one of the very big companies that sells you stuff. And at the time, he and his CIO were saying, look, Amazon has a website, Amazon sells stuff on the website, we have a website, we sell stuff on the website. It's the same thing. But of course it's not. And today, their existence is a little bit in question because of Amazon. So what is it that defines what makes you an internet company if it's not just where you have a website? I've actually been very influenced by Jeff Bezos' speaking on this, but I think the things that define whether or not a company is an internet company is, have you organized your team to do the things the internet lets you do really well? For example, internet companies do tons of A/B testing because we can. We're used to launching 2 products every day and then seeing which one of the 2 versions works better. And so we learn very fast. Internet companies tend to have very short shipping times, very short cycle times. We can ship a new product every week because we can, whereas the traditional shopping mall might reorganize the displays every 6 months or something, or maybe every quarter. So internet companies just learn much faster. We also organize our teams differently. For example, we tend to have a lot more decision-making power pushed down by the engineers and the product managers. Because the internet technology and users are so complicated, only the engineers and the product managers have the information needed to make good decisions. Whereas in a traditional retailer, maybe you can have like the CEO makes all the decisions and everyone do what the CEO says and that's fine, but it doesn't work in an internet company. So this is the rise of the internet era. How about the rise of the AI era? I think a tech company or a hospital or a healthcare system or really any organization plus a few neural networks, this does not make you an AI hospital or company or whatever, or even an AI university or whatever that means. I think all of us are still in the early stages of figuring out what should go on the list on the right. And if you take A/B testing, it took us a long time, right, to realize how fundamental A/B testing would be to the internet. We're still figuring out what should go on the list on the right. But and I am biased, having led some of the great AI teams at Google and Baidu. I actually think Google and Baidu are at the forefront of figuring this out, but I think even the great internet companies haven't fully figured this out. But I think some of the strong candidates for what goes on the right would be strategic data acquisition. The internet teams have been very good at planning out multiple steps, and really, I've been in these teams where we're really playing multi-year chess games, right? Where we're planning out to get this data because we think in a year that lets us build something, that let's get that data, that then lets us do that. And we often make moves that make no sense from an economic point of view, and we do it because we are playing these multi-year chess games to acquire data. AI teams tend to have centralized data warehouses. So this is one that some of you could go home to implement right away if you haven't already. But if you run a healthcare system or something, and if you have 50 data warehouses under the control of 50 different vice presidents, then it'll be impossible for an engineer to get access or get permission from 50 different VPs to access the data and connect the dots. So AI organizations increasingly have centralized data warehouses, although the rise of GDPR and the rise of the international regulatory landscape is getting complicated, and also is a force pulling against that. So we're all figuring that out. We tend to be very good at spotting pervasive automation opportunities. One of the rules of thumb I've given a lot of my teams is almost anything a human can do with less than a second of thought, we could probably now or soon automate. And so I've had a lot of product managers running around my organizations trying to find things that you could do with less than a second of thinking, because that's often a good candidate for automation. And then just as we made up new job descriptions in the internet era, we're making up new job descriptions. Don't have time to go into details, but the way we ask product managers and machine learning engineers to work, the workflow is quite sophisticated and quite different than earlier eras. And then just to wrap up, you know, if the circle on the left represents what AI can do, and if the circle on the right represents what's valuable to healthcare. Because AI technology is still nascent and evolving, to first approximation, only AI experts, you know, have a very good sense today on what's exactly is on the set on the left, and only healthcare experts or domain experts have a very good sense of what exactly is in the set on the right, and we really want to do projects that are at the intersection of these two sets. So in terms of taking AI to healthcare, the approach that I believe works best, and this is true for multiple industries, not just healthcare, but I think that in this era, we should get AI people to learn more about healthcare. You know, so I've been reading a lot, my whole team's been trying to learn about healthcare. We should get healthcare people to learn about AI. But that is slow, and I think in this era, the best performing teams will be cross-functional teams with AI experts and healthcare experts sitting together and working on problems together in this type of, and I think Stanford, I'm fortunate that Stanford has been such a great environment for that. So just to wrap up, right now, I guess my research group is about 35, 40 people. Actually, well, this is a picture of my group. I think we're listening to, that was Matt Lundgren on stage. We're all listening to him talk one day. But we've been fortunate to be working with many projects in collaboration with a lot of great collaborators over in medicine, and it's been this combination of, you know, AI experts, which we represent, together with healthcare experts, working together that I think is enabling us to do a lot of this work. This is just a list of the subset of the projects we're working on. And I think if in the future there are more opportunities for us as AI experts to collaborate with more of you healthcare experts, we would love to pursue those opportunities as well. So let me just wrap up here. And I just can't say how grateful I am to all of our collaborators over in medical school. We just couldn't do this work without them. But let me just wrap up here, and then we'll go to questions. Thank you very much.
Thank you so much, Andrew. That was a wonderful presentation. I think that is a first for us here at Big Data, actually doing live diagnosis on stage. So I hope to see much more of that. Please have a seat here if you want to sit in that one.
Okay.
I'm gonna.
And we're gonna get some of my
yeah, we're gonna bring up
okay,
the students
great.
as well. They're coming, which is great. And so I just encourage you, as before. It looks like somebody might already be there to the microphone. We really want audience participation, so please get your questions. Come up to the microphone. I'm going to take the chairperson's prerogative to ask the first one, and maybe I'll just start with you, Andrew. But you mentioned a little bit at the beginning of your talk about the ceiling that was created by the size of the data sets and the GPU computing. One of the ceilings that has been clear from some of the work that your group and others have been doing is the challenge in the fact that humans often can't agree what the right answer is. We've seen this in some of the work on imaging and electrocardiograms. And how do you, and yet some people have a belief that perhaps the AI can go beyond what a human can do. And I wondered if you could just pick that apart a little bit to, you know, how do we walk down, both for human label data, how do we do that better when humans don't always agree what the gold standard is? And then how do we go beyond even what a human can see to something beyond?
Yeah, let me take a first cut at that and then see if, I think Pranav's been thinking a lot about this, and it's Jeremy Irwin over at the right. So, you know, There are some problems, a lot of diagnostic tasks we even humans can't agree on. And one question I've been asked is people say, hey, Andrew, even humans can't agree on what is the diagnosis, what can an AI do? It turns out that tasks where humans don't agree, those are actually very good candidates for automation. Because if even humans aren't consistent, then often what we find is using an AI allows us to just make more consistent decisions and often higher quality than a single human. It really depends on the domain. And so, for example, one of the metrics we look at is how often do two humans agree, right? And maybe on a task, let's say humans agree 80% of the time. And then you can ask, how often does an AI and a human agree? And if an AI and a human agrees 85% of the time, whereas two humans agree only 80% of the time, I think that's such a strong argument for taking a serious look at maybe, if the AI agrees with your best pathologist, even better than two pathologists agree with each other, then I think we should take a serious look at whether the AI could help suggest or automate some of these decisions. One of the, to get a little bit technical, in machine learning, there's something called the Bayes error rate, which is the optimal best possible error rate, because sometimes the medical sensor just doesn't have enough information to make a diagnosis. Like the information just isn't there. And it's impossible for a human or AI or anything to surpass some level of accuracy that is really limited by the precision or by the resolution of the sensor. But because of that, problems where humans disagree, sometimes there's actually room for the AI to surpass any one typical human's performance, and we're starting to see, in a few narrow verticals, we're starting to see promising signs of that. I don't know if, and in fact, I think Pranav's been working a lot on processes to evaluate problems. Do you want to?
Yeah, maybe just to add on a couple of thoughts to that. One way we can think of this is Dr. A says this is diagnosis J, Dr. B says no, that's this one, not this one. And one idea here is instead of asking one doctor for what they think the right answer is, let's ask 10 of them. And if 6 out of 10 of them say it's A, then let's go with A, and let's consider that to be what we call our gold standard or ground truth. The other approach we're taking to this is often in a lot of imaging, there's this workup process. First, I take an X-ray, and if the X-ray is inconclusive, I take the CT scan. If that's inconclusive, I go to MRI. And what we're finding is, well, a lot of doctors have to do this workup to get to the final answer from the MR scan, for example, or let's say the CT scan if we want to do nodule detection. But now, can we take that answer that we got from the expert looking at some complex modality and apply that same answer to a simple modality like an X-ray, and now train the algorithm off a very simple modality to come up with the same conclusion? And this is an approach to getting around that sort of ground truth problem and being able to train algorithms that are able to match and maybe even outperform radiologists, especially general radiologists, on a task which only subspecialists are so far able to do. And one advantage of that is a lot of these complex modalities like MRIs, those take 45 minutes to do. They cost lots of orders of magnitude as much as an X-ray would. So there's the time benefit and the cost benefit to that.
Great, thank you. Well, we have some questions from the audience, so let's go straight there. Over here first, please. Thank you.
Hi, my name is Ihan, and my background is actually we have about 200 physical examination franchise clinics in China, and we're actually used to be the strategic data acquisition target from Baidu, your previous company. But like you mentioned previously, we have a large pot of centralized data, so we thought we might do this ourselves. And then our fund actually went out for the past couple of years and trying to get some of the great, AI-driven diagnostic companies. We've looked at American companies, we've looked at Korean companies, and they said they have great algorithm, but when we use their algorithm and do our blind test, we found out that, it only matches about like 89% or like 90%. So that wasn't good enough for us to actually use that as a diagnostic tool for our radiologist department. So I was just wondering, do you have any comments on that? What what are we supposed to do as our, the centralized data warehouse? Are we supposed to just be the strategic data acquisition target for like large companies and cooperate with them instead of doing it ourselves?
Great, thank you.
Most AI systems need customization, right? So most data sets are different, and so if you train an AI system on a data set, say collected in the US, I think there's a high chance it would need to be customized to different machine parameter configurations and so on. So often it takes a healthcare expert working hand in hand with a AI team rather than sending data over and then having them apply it. I think that in today's world, how to get the AI teams to work with you is an interesting question. I think our Stanford group here, Stanford's nonprofit, we do work, we just publish papers. So our team here tends to be very open. And so we tend to do work that we share, like the way that Stanford just invents stuff and put it out on the internet. I don't know.
Does someone maybe want to comment a little bit on this idea of precision and recall for these? How good does the AI have to be deployed somewhere, say in a healthcare system where most people are going to be normal and only a small number of people are going to be abnormal? Do you have a comment on that? Yeah. That's part of the question, I think.
Yeah.
I think to answer the question of precision versus recall, it's mostly based on.
Move the microphone a little.
It's mostly a decision based on what's the cost of intervention. If the cost of intervention is something very expensive, then you probably want to focus on a higher precision and keep that as a hard constraint and maximize recall. If it's an intervention which is inexpensive, has no side effects, then you probably want to just focus on high recall, keep that as a hard constraint, and improve.
And there aren't too many of those, unfortunately.
Yeah. Yeah. So.
Great, thank you. Well, let's have another question.
Yeah, and just calling Baidu a strategic data whatever, that's a bit, for what it's worth, the Baidu team is really great. So I do work with them. They're nice guys.
Noted. Let's take another question over here.
Hi, I'm Anthony Chang. I'm a pediatric cardiologist and a relatively old graduate of your biomedical data science program here at Stanford. So thank you for your mentorship and also for really, I think, putting in strong effort into healthcare, which is what we badly need. So I am working on the agenda trying to educate clinicians for AI and data science. I have a question about the Xray project. I noticed that on a relatively straightforward Xray with cardiomegaly, why is the probability, I think 98, 99% of clinicians would say this is cardiomegaly based on a very simple definition. Why is the algorithm yielding a probability only about 0.52? And the second question is, what about a secondary diagnosis with the cardiomegaly? So have you thought about coupling even simple vital signs to the X-ray? Because if the patient had fever, you may want to reconsider the diagnosis of pneumonia, which is pretty far down the list. And if the patient had tachycardia, you might want to consider pericardial effusion, which is probably the most likely diagnosis. So how do you weigh in sort of a secondary diagnosis or a vital sign that might be very, very important to point you in the right direction?
Yep, great questions. I think.
So for your first question about the probabilities that the the algorithm outputs, so that's an issue of what we call calibration, in that the predicted probability is not actually close to the true confidence of the true ground truth. And so this is something that we're actively working on in the lab, is to try to get these algorithms to be more well calibrated. And so they tend to be very good at sort of predicting binary choices. So you set a threshold, let's say 0.4 probability, and then that algorithm would say this person has cardiomegaly. But we're working on trying to do some post-calibration where you actually fine-tune the probabilities and make them closer to the ground truth, so you can actually interpret those confidences correctly. So that's sort of an active project in our group. To your second question, we're also working on trying to integrate clinical diagnoses or clinical findings along with the imaging findings in making these decisions. Because a lot of these pathologies, if you've seen in the X-ray image, sort of require some clinical history. And definitely handicaps the model that they do not have access to clinical history. So this is future work for us to try to integrate clinical history and try to combine that with the image finding to make the most accurate diagnosis as possible.
That's
I think that'll be real.
Maybe just to quickly add on to that. So we have we work with many med school collaborators like Professor Gert Langelotz, Matt Lundgren, Pavik Patel, and really we get together quite frequently to just determine, okay, what is it that we're trying to do in terms of should we take clinical history into account while making these decisions, or should we just make decisions in terms of what we see on the radiograph and present those findings to a clinician who's then able to take into account the patient history and the radiologist's interpretation of the chest radiograph itself in order to come at the decision of the intervention. So how that integration happens is something we're very actively thinking about, and we will continue to think about. But we think that one strategy there is have the radiologist or the algorithm that's doing the task focus on what it can see just off the radiograph.
So we just have 5 more minutes, so I'm going to keep moving, if that's okay, to another question. Thanks.
Hello, I'm Zina Good, a trainee here at Stanford. And my question about large data sets in healthcare. We've been really good at inventing new technologies that now let us get very large data sets of other omics technologies, and such as genomics, gene expression, control of DNA, called epigenomics. So now there is a drive, for example, here at Stanford, for clinical trials to collect all those data types for given patients. And the number of patients is often between 10 and 100. So you can't just apply any of the AI approaches to such data effectively. And in machine learning, there have been success combining multiple data types, such as text and image data, for example. So my question is, if you have any advice on best strategies to approach such data types where we have very deep data, but not that many patients, and we want to predict clinical outcomes.
You know, one of the, it turns out in AI, if you have a giant data set, if you have 1 million data points, 1 million images, say, a lot of AI teams could do well. And you know, many different AI teams will have similar performance. We've seen this in computer vision benchmarks like ImageNet. It turns out when you have a small data set, that's when the performance of a elite AI team actually results in much better performance than the performance of a less experienced AI team. But and it's because when you have a small data set, the details of an AI system architecture, like the neural network architecture, whether the transfer learning, all those details have a much bigger impact. So I think that actually, since you're at Stanford, we're fortunate at Stanford, there's a lot of good AI people. But I think we have some of those collaborators across Stanford. It could be us, could be someone else. Maybe that could help you address these things. Yeah.
Great. Let's take another question.
Thank you. My name is Qi Liu. I'm from the FDA. Great presentation and live demonstration. Thank you, Andrew, and your team. So at the agency, one issue we very often struggle with is what is the most appropriate endpoint for clinical trials. And for example, I work in oncology, and most of the time, survival is the gold standard for clinical trial as an endpoint, but it's not always feasible. So I was very interested to see Alan's work, which you were able to use EHR and using patients' features to predict survival. So I'm just wondering if you ever considered train and test your model in a clinical trial setting, and maybe also augment your data with imaging data. For example, it can capture tumor response to see whether that will perform very well as well.
Those are very interesting suggestions. We do not have the model in a clinical trial yet. However, we are collecting data on more like a prospective trial of how it's been doing at the hospital. And there's definitely scope for including other modalities like imaging and other things, which is currently not being done. Thanks.
Great. I think this might be our last question, unfortunately. Just 1 minute to go.
Hi, I'm Vin. My question is for Anand. Anand, could you talk a little bit about the target variable formulation for your study? And second, have the patients been let known that there's a diagnostic on them, and has there been an analysis on the effects or the implications of the analysis being known to them?
Sure. I'll start with the second one. The predictions of the model is only sent to the palliative care team and nobody else. You can think of it as this whole process being a shortcut for a laborious chart review. So this model is effectively acting as it just shortlists a few people whom the palliative care team still chart reviews instead of chart reviewing everyone.
So there's a selection bias there?
Selection bias. I'm talking about the use case of how the model gets used. Okay. In terms of defining the labels, the version that I spoke about was we treated it as a classification problem, yes versus no. We are now working on more a time to event model, which is more unbiased, where it actually predicts the time to mortality, and it takes basically predictions across all, and then it's easy to convert that into a binary classification, which is less biased.
And how much time are you taking into consideration? Is it like a couple of months or like?
So for the time to event, you can just predict. It's unbounded.
Okay. Thanks.
Great. Well, thank you so much to the audience for the questions. And I think the team will hang around for a little bit afterwards. I hope if they have a few minutes, and if you want to come round to the back and catch them, I think we could talk about this all day. Fortunately, the next session is also on a similar theme. So first of all, though, if you please help me in thanking Professor Ng and the team.